Hello, today we're on 10.7 and we're going to do volume and surface area of similar solids. And the reason we're going to do this is for the problem solving part of our learning standard. So our similar solids are two solids of the same type with equal ratios of corresponding linear measures, such as the length, the height, or the width of the shapes. So we're going to do an example when we're trying to determine if two shapes are similar or not. So today we're going to be working with rectangular prisms. And when we do this, we're going to do the same thing that we did with the triangles when we were determining whether or not they were similar. So we're going to put circles around the sides that go together and then squares around the other sides that go together. And then we can use triangles for the third one. We're going to set up three different ratios or fractions, and each one is going to get one number from each shape. So the circles go together, squares go together, and triangles go together. So for this, we can start with 2 over 2 for the circles, which we know equals 1. And then for the squares, we can do 2 over 4, which we know equals 1/2. And then for the triangles, we have 4 over 8, which is also 1/2. So right away, I noticed that 2 of these are 1/2, but the third one is 1. So because these are not all the same, that means our shapes are not similar to each other. So this one, our answer would be not similar. Okay. So then the next one, we're going to do the same thing. So I'm going to circle the sides that go together, square, and then put a triangle. So these three go together. Oh, and one thing I wanted to point out from the first one, all of the numbers in our numerators came from the same shape. So they all came from the shape that was given on top. And then all of the numbers in our denominator came from our second shape. So you want to make sure you are putting those in the correct spots so that you get the correct answer. So now setting up our ratios for our second pair of shapes, we can start with the circles, which is 2 over 3. It can't be simplified. And then our square could be 2 over 3 again. And our triangle is going to be 4 over 6, which simplifies to 2/3. So now because all of these are the same, that tells us we have similar figures. So that's how you can tell whether or not two shapes are similar or not. Next, we are going to be talking about the ratio of similar solids. So we have already talked about the ratio of the sides. That's just going to be A to B. We are going to then use these to find the ratio of the surface area and volumes. So the ratio of the surface area is going to be the side length squared, just like we did with the area. So A squared and B squared. Next, we're going to have the ratio of the volumes, which is A cubed. Oh, this should be a B. That is a typo. And B cubed. So we just use those side lengths from the original one and we cube them. And the way I remember what I need to do with the side lengths is I think about how would we label our answers for sides, area, and volume. And when we do that, we use units, units squared, and units cubed. So even though when we're doing the ratios, we don't label them with units, we can think about each of these and use them to figure out what we need to do with the side lengths. So if I need to find the ratio of the volume, I know volume is units cubed, so I need to cube those side lengths to find that ratio. Same thing for surface area, except with squared. So now we're going to use this in an example. So we have example 2. The cans are similar with a scale factor of 87 to 100. Find the surface area and volume of the larger can. So we know the scale factor is going to be the ratio of the sides. We have 87 over 100. So now we need to write it as a surface area. So I'm just going to use SA for surface area, and we know we're going to square both the top and the bottom numbers. Now if you square 87 and 100, you're going to get pretty big numbers. So for now, I'm just going to leave it as 87 squared and 100 squared. So because this is the ratio of the surface area, that means it's going to be equal to the two surface areas as a ratio. And we were given that the smaller surface area was 51.84, and we're looking for the surface area of the bigger can. So now we can use this to solve. And if we do that, we can cross multiply. And we're going to have 51.84 times, let's just type this in my calculator, and it's going to be times 100 squared. And again, that's going to give me a big number, which is 518,400, and that is going to equal 87 squared times x, which is 7,569. So then we're just going to solve, and we're going to divide both sides by the 7,569, and that gives us about 68.5 inches squared for our second surface area. And looking back at our surface area of the smaller can, it makes sense that our answer is bigger because the can is bigger, so the surface area should be larger. Now we are going to do the same thing for volume. So for volume, we take the scale factor and we cube those numbers. So again, these are going to get pretty big, so I'm just going to leave them like that for now. So this ratio of the sides is going to be equal to the ratio of the volumes. So we're going to take the 28.27 and put that over, and this time I'm going to use a V because I've already used X. And then we can cross multiply to solve. So if you want to try this one on your own and then hit play, you can do that. If you want to just follow along, you can do that as well. So we're going to take 10 cubed times 28.27. And again, these are going to be big numbers. So that's going to give us 28,270,000 equal to, and then when we take 87 cubed, that will give us 658,503. And that's being multiplied by V. So we're going to take those and we are going to divide both sides by that 658,000. So 28,270,000 divided by our answer. And that should give us 42.9. And that is about equal to our volume. And this one is in inches cubed. And again, when we look at our volume of the smaller can, it makes sense that the volume was less in that one because our can is bigger now. So that's how you can use the scale factors to help you problem solve for surface area and volume of similar figures. So let's look at example 3. The pyramids are similar. Pyramid P has a volume of 1,000 cubic inches. So I'm just going to write that down so I know. And Pyramid Q has a volume of 216 cubic inches. They want us to find the scale factor of pyramid P to pyramid Q. So remember that when we're going 2 goes on top. So we're going to put Q over P. So if we set up a ratio with our volumes, that is going to be 216 over 1,000. So we have 216 over 1,000. And if we simplify that fraction, so right here we're going to simplify, we are going to get 27 over 125. So now we have the volume ratio. So we know the volume ratio. We need to get the scale factor. And if we look back at our notes for this, we know volume is cubed, and we need to get back to the scale factor where it's not cubed anymore. So we're going to do the opposite. We are going to take the cubed root of both parts of the fraction. So to get your scale factor, you're going to take the cubed root of 27 over the cubed root of 125. And we did go over this yesterday of how to type it into your calculator. But if you forgot, you're going to hit the number 3 key, and then you're going to hit the math button. And then you are going to type number 5. And then that will bring up on your screen. It should look like this, where you have 3 and then a square root or a radical sign. So it's the cubed root. So if we type that in, the cubed root of 27 is going to be 3, and the cubed root of 125 is going to be 5. So the ratio, or the scale factor, is going to be 3 to 5, or 3 over 5. And there is our answer. So that's how you can go from having the volume to getting your scale factor. And if this was surface area, instead of taking the cubed root, we would just take the square root of both of the values. So our last example, a store sells balls of yarn in 2 different sizes. The diameter of the larger ball is twice the diameter of the smaller ball. So I'm just going to do this. So the diameter for the larger one is going to equal 2x, because it's twice as big as the smaller one. So this is going to be 2x. And then here's our smaller ball of yarn, and our diameter is going to equal x. If the balls of yarn cost $7.50 and $1.50 respectively, which ball of yarn is the better buy? So I want you to think about this problem and try to figure out which one would be the better buy. Okay. So if you have your guess, now we're going to prove which one is better. So looking at this, we are going to write a scale factor ratio. So our ratio for our sides, I'm going to put the smaller one on top, so that would be x over 2x. And you'll notice we'll be able to simplify this because there's an x in both the numerator and the denominator. So this can be simplified to 1/2. So that's the ratio of the sides. So now we are going to find the ratio of the volume. And the reason we're going to do that is because when we're looking at price, we want to look at cost per how much we're getting. So that's going to be for the volume. So when we do that, we're going to take these numbers and we are going to cube them. So we're going to get 1/8. And for this, on the top, we have the smaller one. And on the bottom, we have the large. So we are going to compare the ratios that we have for the sides, or for the volume. So we have the ratio of 1 to 8. And we are going to compare that to the ratio of the prices. So we don't have that yet, so we're going to write that. So we have 150 over 750. And we can simplify that. 1.5 divided by 7.5. And that's going to give us 1/5. So we're going to compare. If the ratios were the same for the volume and the cost, then that means they would be equal in cost. So we're going to compare ratio of volume to cost. If they were equal, then it would be the same price or same deal, which they're not. We have 1/8 and 1/5. So if we compare the smaller ball to the larger one, the price increases less than the volume increases, because you notice for the volume it goes from 1 to 8, and for the cost it goes from 1 to 5. So you get more yarn for your dollar if you're going to buy the larger yarn ball. So if we have a bigger increase in volume compared to price, then we're getting a better deal by buying the bigger one. So to answer which ball of yarn is the better buy, it would be the bigger one. All right. So those are all the notes for today. If you have any questions, just let me know. Don't forget to look at the next section of 10.8 as well.